Yep, sorry. Yeah, go on.
Sure. So I'll talk about this work on scalable autoregressive 3D molecule generation with a model called Quetzal, which builds molecules in just like how this animation shows. Um, Let me start with like why do we even need 3D generative models as opposed to, just like large language models can generate text or smiles. Um, One thing is that 3D structure is like very general. Like any molecule, complex, amorphous crystal can be represented as just a point cloud of atoms. Um, so it's much more flexible than smiles. 3D structures also directly interfaces with simulation, which means uh, simulation is great because we can use that to turn compute into data. And then lastly, 3D generative models are changing how we do simulation. Like instead of docking algorithms, we can have AlphaFold. Instead of transition state search, like growing string method, we can use generative models that sample that directly generate the transition state, or we can have Boltzmann generators as more efficient samplers of equilibrium distributions. So at least I'll focus on small molecules for now. At least in this field, diffusion models, all atom diffusion models generally dominate 3D molecule generation, whereas autoregressive models have lagged behind. And a lot of the literature stems from this work on equivariant diffusion models. And why would diffusion be dominant? So far, we believe that diffusion is good for spatial modalities like images, or that autoregression can only generate discrete tokens. Um, so on the other side, there are autoregressive 3D generative models. One line of work focuses on symmetry. So, for example, you have an incomplete molecule. You predict which atom to predict the position relative to. Then you predict the atom type. Then you sample the position. Uh, and then you keep building the molecule like so. And they make sure that their predictions are always equivariant to the rotations of the input and permutations as well. Uh, so that's one line of work. Notably, they still discretize positions here. Um, the other line of work is, an XYZ file is just the string. So we can train an LLM to predict ligand conformations or predict like CIF files, crystal structures, or predict um, molecules in this way. Um, so all of that works. One thing is that the generation quality has not caught up to pure diffusion models, and my hypothesis is that maybe it's because of discretization of 3D space, but maybe another reason is tokenization. Um, like there are a lot of tokens here. However, in images, autoregression has caught up to diffusion and it's also faster. So there's this visual autoregressive um, model, uh, which we can see has, you know, comparable FID but much faster inference time. There's also this work on masked autoregression, which is perhaps the basis of this work. And so the core idea taken from the image generation literature is that per token diffusion can enable autoregression without quantization. So here we have a sequence and we're predicting the next token. And so normally in GPT, we have a logic vector encode the categorical distribution for the next token distribution. And we have the transformer understanding the token interdependence. And this has worked very well for all of our language models. But there's no reason that the next token distribution has to be categorical. We can encode that continuous distribution using just some conditioning vector, z here. And then we can, at the same time, train an MLP to generate positions x conditional on z, where x is now some continuous valued token. And so putting that into Quetzal, we have this factorization as the generation, where a 3D molecule is just a list of the atom types, discrete, and the XYZ positions. So when we generate, we'll predict atom type, predict XYZ, predict atom type, predict XYZ, until we predict stop. Now, training is different from sampling because we'll be doing teacher forcing. So at training, we take a full molecule, and then we can we tokenize it naturally into atoms, where we have atom type, and then we have the XYZ value position, a three-dimensional vector for each atom. We can encode those with standard embedding layers or linear and Fourier features. And then we add them together and pass them into a causal transformer. Why causal transformer? This is very similar, actually almost identical to GPT. Causal attention allows us to efficiently batch all of the prefixes together. So really, when we pass in one molecule, we're getting all of these predictions at the same time. And this way we can get loss supervision on every prefix. So to break this down further, one molecule really contains multiple examples, one for each possible prefix of the molecule. So this allows us to train very efficiently. And so far, this is just for predicting the atom type, which is nothing more than a discrete value, which is just like GPT. But now the next part is we can reuse these hidden states in a second transformer, which is also causal, to predict these prefix conditioning vectors, which encode the next XYZ distribution. And we can evaluate this on every prefix with a diffusion loss, which is just denoising score matching conditional on every prefix. And so this diffusion MLP is a very small diffusion model. It's just a three-dimensional distribution. But the nice thing is that all of this can be trained end to end. So I can pause here for questions because that's this is the key point, and like feel free to interrupt if there are any questions.
I have some questions. Can you hear me?
Yes.
Yeah. So how do you balance these different losses? I assume you just sum them up. You have the diffusion loss and the cross entropy loss. Do you reweight them in any way, or?
No, we didn't reweight them. Or sorry, at least cross entropy and diffusion, we just simply add them. We didn't try weighting them separately. But for diffusion, you can weight the sum of denoising score matching losses by for each, like different time steps are more important. And so we use the same elucidating diffusion models loss weighting for that.
Good, thanks. The other question I have is you are making a design choice here. So you predict first the atom type, and then given the atom type, you predict the 3D position using the diffusion approach. You could have done it the other way to predict the 3D coordinates with the diffusion approach first, and then given the 3D coordinates, predict the atom type. Did you investigate both options, or you just went with this one, or?
Yeah, it just never occurred to me to try the other way. But there is a sense in which this is nice because you can force which atom type you're predicting next. which I don't know, seems chemically more intuitive, but
Mhm.
there's no a priori reason.
Good. And then for the diffusion model, just to the last question, I assume you want to have some predictions that are uh, equivalent. Do you enforce that into the model?
That is the next slide. Molecules do have translation, rotation, and permutation symmetries. For these 3D symmetries, we just follow work in the literature such as AlphaFold 3, which will just randomly translate and rotate the training examples. So this soft equivariance by data augmentation, um, in practice, the model learns to make these symmetric predictions. Um, but permutations are um, a trickier matter. Like the data set, it gives us atoms in these XYZ files, and so they're on the computer. They have an order, and this order is usually local. So here this is how the atoms are placed in the XYZ file in order, and notably this ordering is more local. So I tried training the model with random order, and the the task is perhaps just too difficult. So it seems like the order of the atoms contains information. Um,
Could you say a few more words about this order, how it is specified? Like you say, I mean, it's based on these data files, but I assume that the data files already have chosen the order in a particular way. Um,
yeah, typically it comes from Smiles order, I believe. So like you notice that the heavy atoms are placed first, and Smiles is just like a traversal of the heavy atoms graph. And then afterwards, all the hydrogens are placed, um, which I imagine is RDKit's add hydrogens function. Um, but
mhm.
also some of these might be built by hand, and then chemists in like Gauss view would probably build it atom by atom, like locally.
Good, thanks.
Any other questions on this part? Because it's perhaps a little crucial.
Um, Maybe I have another question. So, my question is during generation, if you want to do a conformal generation, uh, just like given the atom types, and you generate its corresponding 3D positions.
Mhm.
So, are you just fixing this atom type to be the atoms you want to generate, and only generate the positions X?
Um, I think that wouldn't necessarily solve it by itself, because you could have the same atom types. Um,
Mhm.
I'm assuming you're referring to the task of like given a smiles, generate a 3D geometry of it.
Yeah.
You could have the same atom types, but then different bonds or like a different ordering, and so it would be a different molecule. So Quetzal doesn't solve the task of conformer search by itself because all it is an unconditional model of 3D molecule sequences or just 3D molecules. But you know, in later work, you can definitely do the conditional distribution of generate 3D molecule conditional on, you know, some kind of prompt. Uh, so currently it
See,
does not do conformer search.
but my question is like, um, when you are only generate the positions,
Mhm.
how do you embed the atom types? Because the atom types you are assumed to be known beforehand.
Um, it just does not solve that problem. Uh, uh, yeah, Quetzal cannot do um,
I see.
conformer search. because there's no way to input the atom types alone.
I see.
Like there's no sense of a prompt here. All it does is just reproduce the training distribution, which is not useful yet, but you know, pre-trained language models, they start by just matching the training distribution, and then we fine-tune them for useful conditional distributions.
Yeah, makes sense. Thank you.
I think there's a chat question. How to explain the causal transformer? So causal here refers to when you predict H2, you can only look at X1 or A1 and nothing else, or as well as X2 and A2, but you cannot look at X3 or A3. And that makes it causal because you're not allowed to look at future tokens to make your current prediction. So if everything were all connected, then it would be very easy, given token 1 to predict token 2, because if this edge were here, then you could just look at the next token and predict it. So we causally mask the attention matrix so that it is triangular, lower triangular, and in this way the model actually has to learn to predict the next token type. And I guess that is a compressed way to say that each prefix to predict the next token is really a separate example, and causal masking allows us to combine all of these in one forward pass. Okay, so then I'll just move on to some comments that this architecture is quite simple. There's no focal atom or relative coordinates. The equivariance is not enforced architecturally, but just by data augmentation. And we don't need to train a separate tokenizer or VAE. And on the flip side, we leverage more standard deep learning components, like leverage MLPs and transformers, leverage hardware efficient implementations of transformers like flash attention and torch compile. So in the results, one thing that's nice about predicting atom type and then predicting position is that we can I guess we can see the atom type here. We can force the atom type, but here is a visualization of the distribution of the next atom type and position at each step of generation. And testing this on QM9, a data set of small molecules.
Sorry, maybe for clarity in the previous figure, could you say a few more words about exactly what is I don't know, explain a bit the figures. For example, I see these crosses. The crosses, I assume, is the atom position. Is that right?
Yes, yeah.
And where do you see the atom type here? Is the color?
The atom type is the color, yeah.
Okay, so for example, let's look at the figure, the second from the left in the middle row. There are one red and one blue cross, the second from the left. Yeah.
Yeah.
So then those are the atom types and the atom positions at the same time, or what?
Yeah, together.
Okay. So then here you are looking ahead 2 steps, no? One to choose the atom type and then the other one to choose the atom position. Is that right?
Yes. Yeah.
And the model is very confident in the prediction of the atom position because I assume you have kind of like a cloud of crosses. Is that right? And they are all on top of each other. Okay.
Yeah. So we notice, I mean, one thing we can notice is that it's very confident, or at least there's not, it could technically predict atom positions elsewhere on this scaffold, but I guess it's following Smile's order, which means the most recent, it's placing an atom next to the most recently placed atom.
Okay, I'm a bit confused when you say following a Smiles order, because Smiles don't have a particular order beforehand. You are using canonical Smiles or some Smile, like the normal Smiles sequences don't have any particular order. They could be specified in any order. So
Yes.
you are
I imagine it is canonical Smiles, but I did not check this for QM9. But it still remains that any Smiles will give, most Smiles gives a local order, assuming you don't like exclusively use ring bonds to denote your Smiles.
Mhm. Okay.
Okay. For QM9, we compared, like, these three models are all atom diffusion, and then the other models are autoregressive models, and notably they all discretize atom positions. So we achieve competitive generation quality on these, stability or validity tests, but at a much greater speed than all atom pure diffusion. And this holds for larger batch sizes, despite the fact that Quetzal has like way more parameters. And some reasons for this is that we're trading off, like SIMDiff is like a diffusion transformer, and every forward pass requires a transformer call to denoise the next step. In Quetzal, we trade those off for more MLP passes, which are cheaper. The second thing is somewhat unfair. We're using the diffusion Hune integrator, which means we just need less diffusion steps. And then the third thing is that flash attention is more efficient compared to EDM, which explicitly materializes these quadratic size messages. So to break that down a bit further, we're trading expensive transformer passes for MLP passes.
Sorry, I have one question. Can you go back to the last slide? Yeah. For the EDM here, are you referring to the equivariant diffusion or the
Equivariant.
Okay, I see.
Not elucidating. Yeah. Right. So for pure diffusion generation, we just iterate over diffusion steps and call transformer. So in total, we have n big N dense transformer passes. But for Quetzal, the generation structure is for each new atom, we have a causal transformer to predict the conditioning vector Z. And then for each Z, we iterate n diffusion steps to generate the position. And so the cost here would be this many MLP passes and then this many transformer passes, where little n is the number of atoms. And so for smaller molecules, this will definitely be faster. Like in QM9, one other thing that we did not add is that we can KV cache this transformer so that generation is faster, but we didn't test that here. So also we tried this on the genome dataset, which contains large or medium-sized drug-like organic molecules. And again, generation is much faster than these other all-atom diffusion models. And another note is that this is the first autoregressive model which is able to scale to these larger molecules. And we obtain competitive, or not the best, but competitive generation quality. So one other nice thing is that Quetzal enables exact density estimation. So for diffusion models, we compute the density of a given data point x0 under this change of variables formula. And the expensive part is this, we have to integrate the divergence, or we have to integrate the trace Jacobian of the neural net of the drift, so the diffusion model. And so this requires a lot of, VJPs, and we have to compute the divergence at every time step. So for pure diffusion, the drift is mapping 3n positions to 3n positions. And so the Jacobian is 3n by 3n, and to evaluate the divergence, we need the diagonal elements, but still we have to compute all of those row by row, and so this is quite expensive. And so we normally have to resort to approximations of the trace Jacobian. But for Quetzal, the diffusion model is mapping 3 dimensions to 3 dimensions, and so we could just explicitly compute the Jacobian at every step. And it's cheap enough that we can explicitly compute it. And yeah, the total sum cost is we trade off transformer calls for MLP calls, and the MLP calls are a lot cheaper. So that gives us a way to compute negative log likelihood of the test set for QM9. We see it's not actually very good on QM9, but it's probably because it's overfitting to the training atom orders, as in the atom types. As in, there are many generation orders, and the one it is learning may not match the same as the test set example. But for Geom, the number looks better, and I think this is because in the Geom split, there are multiple molecules. Each molecule has multiple conformers, and the way that Hugeboom did their train test split is that some molecules have conformers in the train set and the test set. So then the atom ordering would be the same, and maybe this is contributing to better log likelihood here. Was there any question on this part?
I mean, maybe you are going to talk about this later on, but I mean, the log likelihood is interesting. But for example, I mean, it can give you like a metric of quality compared to other baselines. But something that would be interesting is if you have a distribution over 3D atom positions on your training data, if you're actually generating samples that match that distribution. Assuming that you have, for example, imagine that you have molecules where the 3D atom positions are sampled according to some potential energy function, then you may want to see how well your model is learning that.
Yeah.
I don't know if you did any experiments looking into that.
No, we didn't do any Boltzmann generator. Like, we can definitely use this for importance sampling, and that's a great direction for future work, but we didn't try this yet.
Okay.
Okay, and then one other nice thing is that because it's autoregressive, you don't have to specify the number of atoms that you're diffusing over. So we can do any size generation, and so we can get some tasks for free. So on hydrogen decoration, we take a molecule with no hydrogens, and then we add the hydrogens back. This seems trivial, and there are a lot of chem informatics software that does it, but pure diffusion models would struggle for this. Or it's not clear to me how pure diffusion models would tackle this task. But we can see that Quetzal is able to predict at least the correct number of hydrogens and is able to predict their positions with very high accuracy, compared to OLX2, which is a cheminformatics software. OpenBabel is another software, and Symphony is another autoregressive model. And then another task is scaffold completion. So here in blue is the prefix. So we just provide that as the input and allow Quetzal to complete the molecule. And these are some selected examples, but we see that it can do scaffold completion for free, like no additional training, whereas other models might be specifically like trained just to do scaffold completion. And so I guess in summary, scalable autoregression lets us surpass previous autoregressive models and compete with pure diffusion models in quality, while enabling faster generation speed, exact likelihood computation, and arbitrary size generation. One key limitation is that the model is sensitive to the atom ordering. So if we were to take a scaffold and just shuffle the atom order so that it's not very local, then if we provide that as input, the model will fail to generate a valid molecule. So permutation invariance or equivariance here is difficult to solve. So that's in future work, we could just train this on more systems. Something interesting is that the order appears to contain information, and so I wonder if there's some training procedure which could automatically find the best order in which to generate the tokens. And this shows up here where molecules are just an unordered set of 3D atoms, but also it shows up in these autoregressive image models where each image token is a patch, and then you could generate the patches in any order. And similarly for text diffusion, text diffusion seems to struggle relative to autoregressive in terms of quality. Maybe there's like better generation orders. And then another thing is that, as you mentioned, we could use these exact likelihoods for perhaps reinforcement learning or other tailored sampling algorithms to match equilibrium distributions or other desired distributions. But that's everything. The code is available, the preprint is available. There's a Colab notebook that you can scan here to immediately play with. But happy to take any questions.
I have one more question. So you have trained the model using data augmentation to introduce this invariance to rotations and translations, I assume.
Yes.
How important is that? If you switch off that data augmentation, performance deteriorates a lot?
It does.
Do you have?
So here, we tried, smaller models, but this last row is the base model, the largest base model. And then if we ignore this arrow, if we turn off data augmentation, then the stability metrics suffer a lot. And so it seems like, yeah, it is important.
Okay, good. Thanks.
Although I wonder how much data augmentation is necessary, because here, without translations and rotations, is we took all the molecules and aligned them with PCA. So then, like it always sees molecules that are shaped like this and never sees them rotated like this. But I wonder if you just rotate all of them once, and do like a minimal amount of augmentation if that'll still have the same performance.
Yeah. Maybe the other last comment I had is with the ordering. It seems that this ordering in the smile sequences is good, probably because it's a local ordering where you just connect things locally. And yeah, I can imagine if you choose a random order for your sequences, maybe that's not great because maybe there are kind of discontinuities in the order.
Yeah.
One possibility could be to think about using the data augmentation also for training in terms of the order, but consider only not arbitrary random orders, but maybe like some orders that are somehow continuous or some that have some similarity to the training data. Maybe that can also improve things.
Yeah, I actually tried that where like you can compute some orders using, you know, distance matrix and then minimum spanning tree and then traverse that.
Yeah.
But it wasn't very competitive to just the initial generation order.
Okay.
And perhaps the reason is because, you know, the more orderings you have, the larger your data set essentially. And so if you have fixed model capacity, then you're just asking the model to do more work. So I wonder, like, what is the right way? Like, maybe we should just store order as like something important.
I mean, if you use maybe some canonical order, then maybe the model learns that, and that's maybe useful. Good, thanks.
Thank you.
Does anyone else have any questions? Okay, maybe there's no more question today. So let's call it now. Thank you, Austin, again. Thank you for joining us.
Thank you for having me.
Yeah.
Bye.
Thanks,
Bye-bye.
everyone. Bye.
Thank you.
Yeah. Have a good day.